The limit comparison test. Consider a sub n and b sub n, which are sequences of finite positive terms that decrease to 0. And suppose that the limit as n goes to infinity of a sub n over b sub n equals L, where L is positive, has to be greater than 0, and finite, less than infinity. Then the series A and B both converge or both diverge. I often call this in class, if they look the same, they do the same. Well, let's figure out why. Suppose that the limit as n goes to infinity of a sub n over b sub n does equal L, where L is positive, non-zero, and finite. And let's suppose also that our series b sub n converges. What does this mean? So way out in infinity, where it matters, we have that a sub n equals L times b sub n. And let's say this is for n greater than or equal to some value n. That is big N. That means where it matters, n equals big N to infinity of a sub n equals n equals big N to infinity of L times b sub n. But the right side of the equation, since L is a constant, I can pull it outside of my summation, which gives me L times n equals big N to infinity of b sub n. How does that help us? Well, I know that L is finite, because it has to be for the test to work. If my series B converges, then it is finite. And finite times finite equals finite, which means that a sub n converges as well. But suppose that the series B diverges, which means that its value goes to infinity. Once again, where it matters, my series A sub n is L times the series for B sub n. L is finite, but my series of B is infinite, which means that my series for A must be infinite as well, which implies that the series for A diverges. So if I have series that look the same, they do the same. Now we got to be careful about what I mean that they look the same. So let's look at an example. We'll do the series, the summation from 1 to infinity of 1 over 2n squared minus 1. And we're comparing these to known series just like we did with the direct comparison test. So very often we will compare these series to p-series. Not always, but very often. Let's take a look at the p-series 1 over n squared, where p is 2, which is greater than 1, which implies that that known p-series converges. So if I do the limit as n goes to infinity of the sequence parts, so let's say 1 over n squared divided by 1 over 2n squared minus 1, that is, say, b sub n over a sub n. This goes to the limit as n goes to infinity. I'll do the algebra here. I'll rewrite it. I'll flip and multiply the denominator, and that gives me 2. So by the limit comparison test, since the p-series I compared my unknown series to converged, my unknown series will converge also. Quick note, if I had flipped these the other way, I would have gotten a value of 1/2, but that would not have changed anything. Well, is there something that could have changed my result? And the answer is yes. What if I had compared my unknown series to the p-series 1 over n? Which diverges. And then we did the limit as n goes to infinity of 1 over n divided by 1 over 2n squared minus 1. Doing the algebra here as well, I would get 2n squared minus 1 over n as n goes to infinity, but that goes to infinity. And recall that our limit must be positive, can't be 0, but it also must be finite. So if this happens, it simply means you chose the wrong series to compare it to. One more example. Let's do the series n equals 1 to infinity of the square root of n plus 2 over n. Now, can you think of what series we need to compare this to? That is, what does it look like? Well, it looks a lot like root n over n. Certainly at infinity, the plus 2 won't matter. But that simplifies down to 1 over the square root of n. So once again, we have a p-series where the power is 1/2, which is less than 1, which means this p-series will diverge. So I already know that this one's going to diverge, but let's go through the work. Let's do the limit as n goes to infinity of, and I'll put this one on top this time, root n plus 2 over n divided by 1 over the square root of n. Rewriting so we can see this, we would get root n times root n plus 2 over n, which is really close to root n times root n over n, which is 1. So by the limit comparison test, where we compared our unknown to a known divergent p-series, This says that the unknown series must diverge as well.